Welcome back to Science 10. This is the second part in the CD1 section. So here we'll look at climate change, examining the evidence. So is human activity affecting climate? Often in the media we seem to get that impression that it's entirely a human being fault that things are the way it is. So the vast majority of climatologists agree that we are currently experiencing climate change and that human activity has played a role. However, key thing here, we do not yet understand enough about long-term climate cycles or about the interacting factors that control climate to accurately predict the rate at which climate change, to predict the rate of climate change or its consequences. So we don't know the long-term effects. We know short terms. You can see short-term there is something happening, but in terms of hundreds of years, we're just beginning to learn about that. So if we look at the changes in greenhouse gases, so we did that little lab dealing with the greenhouse effect. And of course, the natural greenhouse effect keeps our planet warm by absorbing some of the thermal energy radiated by Earth's surface. Because of course, some of the energy leaves Earth, but greenhouse gases kind of act like a blanket, keeping that energy close to the Earth. The natural greenhouse effect is due mainly to the presence of water vapor in our atmosphere, but other greenhouse gases also play a significant role. And some of these gases are produced by human activity, such as agriculture. So there are four main greenhouse gases. Water vapor is a big one. Carbon dioxide, methane, and nitrous oxide, or dinitrogen monoxide. This table here gives the global warming potential of the three gases. So the global warming potential, or GWP, is a measure of the ability of a gas to trap thermal energy in the atmosphere. Since carbon dioxide is the most common greenhouse gas, it is given a rating of 1. All the other greenhouse gases are then related to carbon dioxide. So if carbon dioxide has a value of 1, gases like methane would have a value of 23. So 23 is able to trap more thermal energy than carbon dioxide. Nitrous oxide, even more. Also, the persistence, the time the gas remains in the atmosphere, is also given. Gases that persist longer will absorb more thermal energy over a longer period of time, of course. So carbon dioxide lasts 50 to 200 years in the atmosphere, methane 10 years, nitrous oxide 120 years. Okay, so a particular molecule will exist that long, potentially. Also, an analysis of ice core samples from Greenland and Antarctica and of atmospheric data collected in the last few decades has led scientists to conclude that the atmospheric concentrations of carbon dioxide, nitrous oxide, and methane have all increased over time period from about 1700 AD to the year 2000. And here we see some graphs here indicated what in fact is going on. So here's the graph of CO2, so 1700 concentration parts per million. So that means if you have a million molecules, how many of those would be carbon dioxide? So we could see it was around 280, but then up close to the year 2000, we have data up to here. And this line here means that they're kind of extrapolating, like predicting how much would happen in between here and here. Okay? So that's what that line represents, kind of an increased prediction as to what happens. If we look at N2O, here we have it here, so not a drastic increase, 0.28 to 0.3, again predicting what's going to happen past that point. Methane, so up until 1950, close to 2000, and then predicting, actually I guess those aren't extrapolation lines, they're atmospheric measurements. Alright, so since greenhouse gases absorb heat, changes in the level of these gases could change the net radiation budget of Earth. So of course that budget was incoming radiation versus outgoing radiation. Increased greenhouse gases levels could mean that less thermal energy is released back into space, and that the average temperature of the Earth's surface would increase as a result. So there'd be more radiation entering and exiting, so the net radiation budget across the Earth as a whole would increase. All right, greenhouse gases, and looking at, okay, human activity. What have we done to have potentially increased the amount of greenhouse gases? So the increased levels in greenhouse gases since the start of the Industrial Revolution in the late 18th century is a direct result of changes in human activity. During this time, human society became more and more dependent upon fossil fuel consumption. That's the key right there. So you can see here we began to use fossil fuels to a large extent. Fossil fuels, of course, fuels that contain large amounts of carbon that were formed from the remains of living organisms. Coal, oil, natural gas are the most commonly used fossil fuels. So first of all, mine fossil fuels and produce them. That releases methane and carbon dioxide in the atmosphere, while burning fossil fuels releases carbon dioxide and nitrous oxide. Now, nitrous oxide is formed when atmospheric nitrogen and oxygen combine when there's a combustion nearby. Okay, so that's how nitrous oxide is actually formed, through carbon combustion from fossil fuel combustion. The most significant increase in concentration of gases from fossil fuel combustion has been carbon dioxide. Any process that releases carbon dioxide to the atmosphere is called a carbon source. So fossil fuel is one such item. It's a carbon source. It contains carbon which is released. Burning fossil fuels is a carbon source since it releases carbon dioxide to the atmosphere. The respiration of living things is also a carbon source since this process releases carbon dioxide to the atmosphere. So you and I, of course, release carbon dioxide just through the process of breathing. At the same time, people were migrating into the wilderness areas and clearing land for forest to provide timber for fuel and construction, to prepare areas for agriculture. And of course, as we've seen earlier, forests play an important role in removing carbon dioxide from the air through photosynthesis. So plants take in carbon dioxide and make oxygen. So photosynthesis is referred to as a carbon sink, which is a process that removes carbon dioxide from the atmosphere. It's just like you dump a drink that you don't want down the sink, it sucks it up. These items are referred to as carbon sinks because they remove carbon from the atmosphere. Large amounts of carbon dioxide dissolved in the Earth's oceans and lakes are removed from the atmosphere. So, of course, we looked at that too. Oceans and lakes are also a carbon sink. They remove carbon dioxide from the atmosphere and cause it to settle on the bottom, helping to make shells, etc. This process is also an important carbon sink. The loss of forest cover during the last two centuries reduced the size of Earth's carbon sinks and therefore decreased the amount of carbon dioxide removed from the atmosphere. Loss of forest cover continues today. So removing plants, trees, etc., we're removing how we can remove carbon from the atmosphere. When the release of carbon dioxide to the atmosphere by carbon sources is equal to the amount of carbon removed by the atmosphere by carbon sinks, such as forests, plants, oceans, the amount of the greenhouse gas remains stable. So we can see there's kind of a balance here. If I'm releasing carbon and absorbing carbon at the same rate, there's a balance to the atmospheric gases. But of course, however, the balance between carbon sinks and carbon sources has shifted since the Industrial Revolution, causing levels of carbon dioxide in our atmosphere to increase. According to scientists, the Carbon Dioxide Information Analysis Center in the United States, the concentration of carbon dioxide gas in the atmosphere has increased by 32% over the last 200 years. So that's quite huge. Over the last 200 years, the amount of carbon dioxide in the atmosphere has increased by 32%. So the amount that's released is way more than the amount absorbed. Okay, so yes, humans have played an effect in greenhouse gas release. Agriculture is another human activity, but what I think I'll do there, the video is almost at 9 minutes, so I think I'll stop there, and in part 2 we'll look at this second part. Okay, we'll see you again.